Now let's look at our first topic in this lesson, topic A, future engineering for regression. Future engineering is the process of taking data and transforming it for use in predictions. The idea is to create futures that capture aspects of what's important to the outcome of interest. This process requires both data expertise and domain knowledge. You need to know what can be done with the data that you have, as well as knowledge of what might be predictive of the outcome you're interested in. We will first look at how to transform data to create futures, and then how to clean the data of the resulting futures to ensure models are trained on high-quality data. In order to perform a regression, we first need data to be in a format that allows it. Futures are transformed versions of the data that capture what we think is possibly predictive of our outcome of interest. For example, if we are trying to build a model that will allow us to predict a customer's spend for the next year using data for the current year, we will need two historical periods to build our model. One period where we already know the customer spend, and another earlier period that we will use to calculate futures. We can then build a model that uses the futures from the earlier period to predict the outcome in the later period. This model will then be able to use futures created using data we have at present to predict an outcome about a future period. The following figure illustrates the role of future engineering in a machine learning workflow. Generally, future creation and data cleaning go hand in hand. As you create your futures, you might notice problems with the data that need to be dealt with. The following are common problems you will notice with data. Data could be missing. The easiest way to deal with missing data is to just remove those data points that are missing some data if it makes sense to do so. Otherwise, you can attempt to insert a value for a missing variable based on the average or median of the other data points. Outliers could be present. Outliers are data points that lie far outside of the normal range of a variable, or in other words, far from the norm. A standard deviation is that an outlier is any data point more than 3 standard deviations above the median. They are dangerous because they might not reflect normal behavior but can have a disproportionate effect on our model. Again, the easiest method of dealing with outliers is to simply remove them. And now it's time to do an exercise. Creating futures for transaction data. In this exercise, we have some historical transaction data from 2010 to 2011. For each transaction, we have a customer identifier, which is a customer ID, the number of units purchased, which is quantity, and the date of the purchase, which is invoice date, and the unit cost, unit price, as well as some other information about the item purchased. We want to prepare this data for a regression of customer transaction data from 2010 against the spend for 2011. We will therefore create futures from the data for the year 2010 and compute the target, the amount of money spent, for 2011. When we create this model, it should generalize the future years for which we don't have the result yet. So we could use 2020 data to predict 21 spending behavior in advance, unless the market or business has changed significantly since the time period the data used to fit the model relates to. And as a first step, we are going to import pandas and read the data from retailtransactions.csv to a data frame df. Now let's use the head function to view the data. Now we are converting the invoice date column to date format using the following code. Now with this code, we are calculating the revenue for each row by multiplying quantity with unit price. You will observe that each invoice is spread over multiple rows, one for each type of product purchased. These can be combined such that data for each transaction is on a single row. To do so, we can perform a group by operation on invoice number. However, before that, we need to specify how to combine those rows that are grouped together, and we are using this code for that. In this code, we first specified the aggregation functions that we will use for each column, and then performed group by and applied those functions. Invoice data and customer ID will be the same for all rows for the same invoice, so we can just take the first entry for them. For revenue, we sum the revenue across all items for the same invoice to get the total revenue for that invoice. Finally, we are going to use the head function to display the results. You should also see this output in your computer. Since we will be using the year to decide which rows are being used for prediction and which we are predicting, we are creating a separate column named year for the year, and we are using this code for that. The dates of the transactions may also be an important source of futures. The days since a customer's last transaction as of the end of the year, or how early in the year a customer had their first transaction, can tell us a bit about the customer's purchasing history, which could be important. Therefore, for each transaction, we'll calculate how many days difference there is between the last day of 2010 and the invoice date. Currently, we have the data grouped by invoice, but we really want it grouped by customer. We will start by calculating all of our predictors. We will again define a set of aggregation functions for each of our variables and apply them using group by. We will calculate the sum of revenue for days since. We will calculate the maximum and minimum number of days, giving us futures, telling us how long this customer has been active in 2010 and how recently, as well as the number of unique values, giving us how many separate days this customer made a purchase on. Since these are for our predictors, we will only apply these functions to our data from 2010, and we will store it in a variable, x, and use the head function to see the results. I hope you also see this result in your computer with me. As you see from this result, because we performed multiple types of aggregations on the days since column, we ended up with multi-level column labels. To simplify this, we can reset the names of the columns to make them easier to reference later. We are using this code for that. Now we will calculate one more feature, the average spend per order. We can calculate this by dividing revenue sum by days since and unique. This is really the average spend per day, not per order, but we're assuming that if two orders were put in the same day, we can treat them as part of the same order for our purposes. Now that we have our predictors, we need the outcome that we will be predicting, which is just the sum of revenue for 2011. We can calculate this with a simple group by and store the values in the y variable with this code. Now we can put our predictors and outcomes into a single data frame, wrangled df, and rename the columns to have more intuitive names. Finally, look at the resulting data frame using the head function. Note that many of the values in our data frame are NaN. This is caused by customers who were active either only in 2010 or only in 2011. So there is no data for the other year. In a future lesson, we will work on predicting which of our customers will churn, but for now, we will just drop all customers not active in both years. Note that this means that our model will predict the spend of customers in the next year, assuming that they remain active customers. To drop the customers without values, drop rows where either of the revenue columns are null. As a final data cleaning step, it's often a good idea to get rid of outliers. Now that's a long code, but you can find this code in your exercise 20 file. A standard deviation is that an outlier is any data point more than 3 standard deviations above the median. So we will use this to drop customers that are outliers in terms of 2010 or 2011 revenue. It's often a good idea, after you've done your data cleaning and feature engineering, to save the new data as a new file so that as you're developing your model, you don't need to run the data through the whole feature engineering cleaning pipeline each time you want to rerun your code. Now we can do this using the toCSV function. We can also take a look at our final data frame using the head function. I hope this exercise helped you understand data cleaning and feature engineering using Python. Now let's turn back to our lesson. Once we have our features of interest created, the next step is to assess those futures, which can be done in the following sequence. First, we should do a sanity check of our futures to make sure their values are what we would expect. We can plot a histogram of each future to make sure the distribution of the future is also what we would expect. This can often reveal unexpected problems with our data. The next step is to examine the relationships between our futures and the outcome of interest. This can be done creating scatter plots. Often, the most effective means of assessing a relationship is to create a scatter plot that plots a future against the outcome of interest and see whether there is any obvious relationship. Another quick and effective method for assessing a relationship is to see whether there is a correlation between the variables. Correlations are linear relationships between two variables. They can be positive, as one variable increases, the other increases, or negative, as one increases, the other decreases. Correlation can be calculated easily using statistical packages, resulting in a single number that can often reveal whether there is a strong relationship between two variables. The figure that you see on the screen illustrates the different correlation from perfect positive to perfect negative correlation. Let's go ahead and do an exercise about this subject. In this exercise, we will use the futures we calculated in the previous exercise and see whether these variables have any relationships with our outcome of interest. We use pandas to import the data that we saved at the end of last exercise using customer ID as the index. The Seaborn library has a number of nice plotting features. Its paired plot function plots the histograms and pairwise scatter plots of all of our variables in one line, allowing us to examine both the distributions of our data and the relationships between the data points easily. We use the code that you see on the screen. Now you should also get the following plot when you repeat this step. Now the diagonal shows a histogram for each variable, whereas each row shows the scatter plot between one variable and each other variable. The bottom row of figures shows the scatter plots of the 2011 revenue, our outcome of interest, against each of our other variables. Because the data points are overlapping and there is a fair amount of variance, the relationship don't look very clear-cut in the visualizations. Therefore, we can use correlations to help us interpret relationships. Again, we can look at the last row to see the relationship between our predictors and outcome of interest, 2011 revenue. Positive numbers indicate a positive relationship. For instance, the higher the 2010 revenue from a customer, the greater the expected revenue from them in 2011 should be. Negative numbers mean the reverse. For example, the more days there have been since a customer's last purchase, the lower we would expect the 2010 revenue from them to be. Also, the higher the absolute number, the stronger the relationship. This was a quick but very useful exercise, and I hope it helped you understand this concept better.